Today we're going to talk a little bit about a strange thing that happens with water that only a tiny fraction of water molecules do this. Now, if you look at the slide, it says that in 1 liter of water, 1 out of every 554 million water molecules does something very weird. And if you're wondering, well, what can it do? Well, a tiny, tiny fraction of all those water molecules will spontaneously break apart. They will break apart into a hydrogen ion and what's known as a hydroxide ion. A hydroxide ion is simply oxygen and hydrogen with an extra electron. And if you look at what a hydrogen ion is, since hydrogen typically just has 1 proton and 1 electron, if you remove the electron, which makes it a positive ion, pretty much the only thing you have left of the atom is going to be a proton. So sometimes hydrogen ions are just called protons. This process of a water molecule splitting in two and becoming a hydroxide ion and a hydrogen ion is called dissociation. Dissociation. That's the splitting of a molecule into two parts. Sometimes if you look in other fields, for example in psychology, there are certain psychological disorders that are called dissociative disorders, where a person breaks with reality. All right. That's where similar word root or definition for what we have in chemistry. Now, what will happen is just a tiny, tiny fraction of those water molecules will do that. And they'll dissociate into a negative hydroxide ion and a positive hydrogen ion. Right. Now, in chemistry, those hydrogen ions don't stay single very long. In real life, they go off and bond to another water molecule and form an ion that has 3 hydrogens to it. And this is called a hydronium ion. Right? And as you can see, it's H30 or H3O, sorry, that has a positive charge. In chemistry, that's what we usually refer to as the hydronium ion concentration. All right? That's a measure of how many water molecules have actually dissociated. But in biology, we're going to keep this a little simple, and I'm just going to refer to hydrogen ions as if they're just out there single. But in reality, those hydrogen ions will often go and bond to a water molecule, forming what we call a hydronium ion. Now, water isn't the only thing that will dissociate. There are plenty of other compounds and molecules that will do this. So a special group of compounds that will do this are what are called acids. Acids are substances that will dissociate, they'll break apart, and one of the products of that will be a hydrogen ion. So acids are defined as molecules that dissociate when you place them in water and release hydrogen ions. All right. We define an acid as something that increases the hydrogen ion concentration of a solution. All right. So we say that pretty much any substance that goes and increases the hydrogen ion concentration of a solution is classified as an acid. Now, one of our most famous acids, in fact, this acid is found in your stomach. This is what makes up stomach acid, is hydrochloric acid. You see that formula HCl. hydrochloric acid. This is a strong acid, and when you place it in water, it will readily dissociate into hydrogen ions and chloride ions. So that's what acids do. They increase the hydrogen ion concentration in a solution. So when we add them to water, they will readily dissociate. Well, some more than others. And we'll talk a little bit about strong acids and weak acids. Now, the acids that you probably know about are the strong acids. For example, if you look at the acid that's in your car battery, that is a great example of a strong acid. That's called sulfuric acid. All right. There's another common acid that's called nitric acid. All right. Those three are good examples of strong acids. And what we mean by a strong acid is an acid that when you place it in water, right, most of the molecules will dissociate and release hydrogen ions. That's what we mean by strong, is that they will readily dissociate. So if we put hydrochloric acid in water, it will readily dissociate into hydrogen ions and chloride ions. All right. So most of those molecules will break apart. Now, you'll notice that we have some other acids there as well. These are called weak acids. And weak acids are ones that when you place them in water, maybe about 1% of them will dissociate. All right. So 1%, all right, not all of it, like a strong acid. So just a fraction of them, maybe about 1% of these weak acids will dissociate in water. And some good examples of this, for example, a little bit later we'll talk about carbonic acid. This is the stuff you find in seltzer water. It's a weak acid. Acetic acid you may know as vinegar. When you eat a lemon or a lime or an orange or a tangerine, the sour flavor comes from citric acid. This is often an additive to soft drinks. If you like to drink Sprite or other lemon lime sodas, you'll find that one of the flavorings is citric acid. If you were a fan of Sour Patch Kids or sour worms, the principal sour taste comes from citric acid. A couple other ones, phosphoric acid. This is often an additive for flavoring when it comes to certain types of sodas and soft drinks. For example, a lot of grape-flavored soft drinks have phosphoric acid. And here's one, oxalic acid. This is one that we find in leafy vegetables like spinach. But all these weak acids, as we know, only about 1% of the molecules in a weak acid, when added to water, will dissociate. So that's the difference between strong acids and weak acids. Strong acids will dissociate a whole lot more. Now, acids have some physical characteristics. They're found in a lot of substances. In fact, a lot of our diet has acidic components to it. The one thing that is characteristic of acids is that they taste sour. On our tongues, we have a special little receptor that detects hydrogen ions. And the hydrogen ions, when they go and bond, will actually go and trigger that sour flavor. All right? So the more sour something is, usually the more acidic it is. We know as a definition that acids will produce hydrogen ions in solution. They'll release excess amount of hydrogen ions. We have several different indicators for pH. One of the early ones was called litmus paper. And basically, a lot of plant pigments will change color when it comes to acids or bases. And what they'll do is they'll take this plant pigment, put it on a little piece of paper, and then when they want to test something to see if it's acidic or whether it's basic, we dip it in there. And litmus paper has been around for a long, long time, and characteristic litmus paper will turn red in acids. And in one of our labs that we'll do, we'll actually go and do some testing. We'll use another plant pigment, and we'll indeed see that acids go and change the color of the plant pigment, and we can tell how acidic something is or how basic something is by the color change. One remarkable thing about acids is that they are incredibly reactive with metals. And in fact, when you go and you put an acid, particularly mix an acid with usually a strong acid with a metal that has been ground up in a powdered form, they will often react vigorously and produce hydrogen gas. And a great example of that is powdered zinc. So if you take, for example, hydrochloric acid and mix it with powdered zinc, it will bubble and foam and it will release hydrogen gas. And because of all the hydrogen ions and the negative ions, they're incredibly reactive, so we often find that acids are quite corrosive. Now, on the other part of the spectrum, we have what are called bases. These are often referred to as alkaline substance or alkalis. Bases do sort of the opposite of what acids do. We saw how acids go and increase the hydrogen ion concentration. Bases, on the other hand, will reduce the hydrogen ion concentration in a solution. Bases, just like acids, when you add them to water, will break apart, will spontaneously dissociate into a positive and negative ion. A great example of a base is a strong base. This is called sodium hydroxide. That's what the NaOH stands for. Sodium hydroxide is commonly known as lye. You may have heard of lye. Lye is a very strong base. We use it for a lot of things. In the old days, when they still do it, I use lye to actually go and make soap. If you go and take a look at Drano or Liquid Plumber, any of those things that help clear your drains chemically, that's lye. It's found in a lot of our cleaning products as well. So it's been around for a long period of time. If you put sodium hydroxide or lye in water, it will spontaneously break apart into sodium ions and hydroxide ions. All right. So it will dissociate. Now the thing is that what bases do is they reduce the hydrogen ion concentration of a solution. So you might be wondering, well, how does that do that? Well, let me show you. So let's imagine we have some sodium hydroxide and we've placed it in water. And remember, the water, a tiny fraction of the water has already dissociated. And so we have some hydrogen ions and some hydroxide ions. Well, when you add more hydroxide ions, they're always looking for something that's positive. And so in that case, those hydroxide ions will often pair up with the free hydrogen ions that are already present in water and make water. So in this case, what you see is the hydroxide ions pairing up with the hydrogen and returning and reducing the hydrogen ion concentration. So that's what bases do. Bases reduce the hydrogen ion concentration lower than what we have with just plain water. So if a hydrogen ion concentration of a solution is less than what water has naturally, then we say that it's a base. So that's how bases work. They reduce the hydrogen ion concentration. And of course, like anything, we have strong bases and weak bases. And here's just a couple of examples just to show you. Now, most people are familiar with acids, but not as familiar with bases. The first one we've talked about before is sodium hydroxide. This is classified as a strong base. If we place it in water, it will almost completely dissociate. We find it in oven cleaner. If you've ever used Easy Off to go and clean your oven, that one has sodium hydroxide. A lot of cleaning products, Formula 409, has sodium hydroxide in it. Potassium hydroxide, KOH, is actually quite fascinating. This is often made into fertilizer. We often use it to make soap. There's a fascinating way to make potassium hydroxide. Oh, excuse me, I was thinking about sodium hydroxide. There's another interesting base called sodium hydroxide. And sodium hydroxide is actually made by taking ashes from burned hardwoods. So, you know, oaks and things like that. When you go and burn the ashes and then you just let it soak, those ashes soak. Over time, what happens is the sodium hydroxide starts forming, and you get a nice little source of that. And oftentimes what they'll do is they'll take that fluid and they'll let it dry out so crystals are formed, and the sodium hydroxide will come out as a crystalline form, and then you have a nice little case of a strong base. And this strong base is actually used easy way to actually go and make soap. You just add some fat. In the old days, if you go to the Appalachians and places before, they would take lard and mix it with sodium hydroxide and use that to make soap. Calcium hydroxide is an interesting one. That's actually fairly easy to make. We saw how you can make a strong base using the ashes of hardwoods, but you can also make a very useful strong base by pulverizing limestone or pulverizing oyster shells or clam shells, and then heating that up. And that will create a thing called calcium hydroxide. Calcium hydroxide is commonly known as lime, L-I-M-E. And lime is used for a lot of different things. For example, in places where they have a lot of deaths, for example, if you think about World War I, where millions of people were killed, on the battlefield they would often go and have to make these mass graves, and to keep the stink down and the stench down, they would often go and cover the bodies with lime, and that strong base would often go and kill any type of little organism like bacteria that were causing the stink. As you can see, if you've ever had Nair to remove leg hair or body hair, that's basically calcium hydroxide. Now we have quite a few little weak bases as well. Milk and magnesia when I was a kid, and then I would have an upset stomach or heartburn. This is what my mother gave me. Ammonia, believe it or not, is a wonderful base. It's considered to be a weak base. Weak bases, just like weak acids, only dissociate a little bit, so maybe 1% of the total base molecules will dissociate when added to water. But ammonia is a very, very classic one. We often use it for cleaning products, and ammonia likes to go and pick up excess hydrogen ions, so it reduces the hydrogen ion concentration. Baking soda, washing soda, sodium bicarbonate, sodium carbonate are fantastic, fantastic little bases. Now, bases can be identified in a couple of different ways. One is by taste. They can taste bitter. All right. Unlike acids that taste sour. We eat a lot of acids, but we don't eat a lot of bases. One really important one that I often use if I suspect that I have a base on my fingers, I will rub my fingers together to see if it feels slippery or soapy. Oftentimes bases will feel this way, and if I do feel it like a little slippery, then I'll also go and rinse off my fingers. Unlike acids, which will go and turn litmus paper red, it'll turn blue in a base. And so a great little test, and oftentimes we use it in as a common parlance. For example, I've often heard in politics that, you know, to be a good Democrat, the litmus test is someone who supports increasing the minimum wage. All right, so litmus test is something that you'll hear, but basically the litmus test is a way to test if something is an acid or a base. Now, just like acids, bases will also react vigorously with metals, particularly powdered metals, but instead of releasing hydrogen gas, they actually go and produce a precipitate, a little materials inside, substances inside that solution will actually become insoluble and fall out of solution. We call that a precipitate. Now, acids and bases are classified on how acidic they are or how basic they are by their concentrations of hydrogen ions. Now, we saw that since acids release excess hydrogen ions and bases remove hydrogen ions from solution, that's a good way to classify them as you know, how much hydrogen ions there are in a solution. Now, in chemistry, we have a unit of measurement. All right. Now, a lot of different things have units of measurement. For example, if you're a baker, you know, the unit of measurement for a baker would be a dozen. All right. If you are play football, or you're a football coach or a football fan, the unit of measurement is a yard. All right. Now, for chemists, the unit of measurement is a quantity called a mole. A mole is used in chemistry all the time. We're often going and converting moles to grams and grams per mole and all kinds of stuff. In fact, this is often part of the frustrating part of the first semester of chemistry, is measuring concentrations of different chemicals in compounds and substances. And so a mole basically is the weight of a substance measured in grams, all right, that corresponds to the atomic masses of all the atoms in a molecule of that substance. All right. Let me break that down to you. If you look over there on the right on the graphic, you'll notice hydrogen has 1 gram equals 1 mole. So if you had, for example, 1 gram of hydrogen, you would have 1 mole of hydrogen. Right? Now, where did we get that number? Well, it turns out that hydrogen, as you know, has an atomic mass of 1. And what we mean by a mass, atomic mass, is it's the number of protons plus the number of neutrons in the nucleus. So that's what the atomic mass is. It's the number of protons and the number of neutrons. Now, the most common type of hydrogen, what makes up most of the hydrogen in the universe, has 1 proton. So it has no neutron. So its atomic mass is just 1. So if we had 1 gram of hydrogen, that would be 1 mole of hydrogen. Or if we go the other way, if we have 1 mole of hydrogen, that would weigh 1 gram. let's look at carbon. Now, carbon, as you know, has 6 protons and 6 neutrons. All right? So its atomic mass is 6 plus 6, that's 12. So 1 mole of carbon would weigh 12 grams. So if we had 12 grams of carbon, that would be 1 mole of carbon. Oxygen, for example. Oxygen has 8 protons, 8 neutrons. 8 plus 8 gives us 16. So we have 16, that's the atomic mass. So if we have 1 mole of oxygen, that would weigh 16 grams. So if we had 16 grams of oxygen, that would be a mole of oxygen. Now, so if 1 mole of hydrogen is equal to 1 gram, how many moles of hydrogen are there in 1 liter of pure water? All right. So here we have a liter of water, and we want to know how many moles of hydrogen there are. And if 1 mole is equal to 1 gram, all right, then we know how to calculate that. Now, if you remember when we started this lecture that only 1 out of every 554 million water molecules dissociate in a liter of water. All right. So it's going to be a tiny, tiny, tiny amount. All right. When we say 1 in a million, that's pretty small. But when we say 1 in 500 million, that's even less. All right. So the concentration in moles is going to be very, very small. And it turns out that in 1 liter of pure water, we're going to have 0.0000001 moles of hydrogen ions. All right, that's tiny, 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 tiny. All right. Most water molecules don't dissociate. Just a tiny fraction of them. So in a liter of water, we just have a little trace amounts of ones that dissociate, trace amounts that dissociate into hydrogen ions and hydroxide ions. Now, since water splits apart into equal amounts of hydrogen ions and hydroxide ions, that's the same amount for hydroxide ions. If we measured the hydroxide ion concentration, it would be exactly the same, 0.0000001 moles of hydrogen ions. Right. Now, in math, when we're playing with things with a big number or a small number, instead of having to keep track of all those zeros just visually, we use scientific notation. So down below is the same number that you see there written in scientific notation. So 10 to the minus 7th moles of hydrogen in 1 liter of water. All right? So that's the concentration. All right? So 10 to the minus 7th. Now, how we come up with that minus 7th, if you haven't had a lot of experience with scientific notation, is that's the number of decimal places. So if you start back there with 1 and go to the right of it and say, okay, there's the decimal point, I'm just going to move that 7 places. And if you make it 7 places, you get 0.0000001. So that's why it's negative. All right. So in that case, those count for the number of decimal places. So really, really small. Now, if we go and we look at a lot of substances, all right, we are surrounded and we use a lot of things that are acidic and basic. It's part of our everyday life. It's part of the world. And you'll notice that right here in the middle we have water. This is just regular. We could say it's tap water. We could say that it's spring water. We could say that it's distilled water. All right. Water has a concentration of 10 to the minus 7th moles per liter. So I have it written out both ways, all right? Scientific notation and then just a straight decimal. Now, if you look, there's quite a few other little things. For example, let's take a look at saliva. All right? Turns out your saliva is also a little acidic. And for our cases, we're going to say our saliva has 10 to the minus 6 moles per liter of hydrogen ions. So let's imagine that it has 10 to the minus 6. So if you look at it and you go, wow, 10 to the minus 6, and you go and you look over at where it's written out as a decimal, you'll notice that it has one less decimal point. That means every decimal point is 10. All right? So the difference in concentration between something like saliva and water is that saliva has 10 times more hydrogen ions than water does. Okay. Now, if we go down to coffee, black coffee, the freshly made coffee, has 10 to the minus 5 hydrogen ions per liter. That's the concentration. All right? And so, as you can see, it has one less decimal point, decimal place. All right? So, compared to water, you'll see that black coffee has 100 times more hydrogen ions. Each step in our little scale here is a 10-fold difference in hydrogen ion concentration. So we can say that saliva is 10 times more hydrogen ion concentration than water. We could say that black coffee has 100 times more hydrogen ions than water. Let's jump down to, let's say, a Coke. If you drink a Coke or a soda, you usually find that it has a hydrogen ion concentration of 10 to the minus third. All right, 10 to the minus 3. Now, if we think about that 10-fold difference, all right, we can count it up. We say, okay, 10 to the minus 6 would be 10, 10 to the minus 5 would be 100, 10 to the minus 4 would be 1,000, 10 to the minus third would be 10,000. So, Coke has 10,000 times more hydrogen ions than water does. Right? So each step is a 10-fold difference. And when we're going down the scale, something that's more and more concentrated, all right, for every decimal space, we're going to add 10 to it. So Coke would be 10,000 times more acidic or more hydrogen ions than water. Now, the one that's the biggest, as you can see, if we look at stomach acid, which has about a tenth of a mole of hydrogen ions in it. All right. Now, if we count the number of decimal places, all right, so we start at minus 7 and go to minus 1. So minus 6 would be 10, minus 5 would be 100, minus 4 would be 1,000, minus 3 would be 10,000, minus 2 would be 100,000, minus 1 would be 1,000,000. So if you look at something with 10 to the minus 1, that would be 1,000,000 times more hydrogen ions than water. Right? Now, if we go the other way, toward the base side, you can see that we use the same thing. For example, let's say we look at seawater. Seawater has a hydrogen ion concentration that's less than water. And we'll assume that it has 10 to the minus 8. Now 10 to the minus 8 versus 10 to the minus 7, that's a whole decimal place. So we find out that seawater has 10 times less hydrogen ions than water does. 10 times less. So every step you'll see is a tenfold decrease in hydrogen ion concentration. If we look, for example, at borax at 10 to the minus 9th, that would be 100 times less hydrogen ions than water. If we look, for example, at milk and magnesia, all right, that would be, let's see, 10, 100, 1,000, that would be 1,000 times less hydrogen ions than water. If we go clear up to, let's say, sodium hydroxide at 10 to the minus 13, all right, so if we count, all right, 10 to the minus 8 is 10, to minus 9 would be 100, to minus 10 would be 1,000, to minus 11 would be 10,000, to minus 12 would be 100,000, to minus 13, that's 1,000,000. So sodium hydroxide would have 1,000,000 times less hydrogen ions than water does. All right? So, as you can see, between the exponents, there's a tenfold change. Now, playing with numbers that are exponents, you know, minus 9, minus 5, minus 2, is a little bit tricky. So a Danish chemist named Sorensen came up with an easier way to measure the hydrogen ion concentration. And what he did was just a transformation using some algebra. If you take, for example, 10 to the minus 7th, and then on your calculator you punch in the negative natural log of 10 to the minus 7th and hit the equal button, it will pop up 7. If you take, for example, let's say household ammonia at 10 to the minus 12, if you go and you punch in 10 to the minus 12 and then you hit the negative natural logarithm of that on your calculator and then hit equal, the number that appears is 12. If, for example, you take 10 to the minus 4, that is the hydrogen ion concentration of wine, right? And then on your calculator, punch in 10 to the minus 4 and then hit the negative natural logarithm of that and hit equal, you'll get 4. Right? What he did was change the scale. He created something that we use to measure hydrogen ion concentration. He created what we call the pH scale. Right? So instead of saying that water has a concentration of 10 to the minus 7th, right, now we just say water has a pH of 7. All right? Now, it's very easy to switch from one measurement to the next. All right? So, for example, if we say that milk of magnesia has a pH of 10, what would be the hydrogen ion concentration in moles per liter? Well, you just think, well, if it's 10, then it just has to be 10 to the minus 10. You just go and flip it back to its exponent. Really simple. For example, if you have something that's a pH of 5, that would be 10 to the minus 5. Right? If you have something that has a pH of, let's say, 1.5, what would be in moles per liter concentration? Well, that's easy. That would just be 10 to the minus 1.5. All right? So the pH is simply just the exponent times minus 1. All right? That just turns it into a whole number. All right? So as you can see, when we look at acids, acids are any solution or any substance that has a pH less than 7. And when we look at bases, or sometimes called alkalis, they have a pH that's going to be bigger or greater than 7. All right. So we usually say that acids range from 0 to 7, and that bases range from 7 to 14. But it turns out if you go out and take chemistry, you'll find out that there are solutions out there, substances that have negative numbers that go beyond 0 and go beyond 14. All right? It doesn't end at 14, and it doesn't end at 0. All right. So, now you might be wondering, well, where did it get the name pH from? All right. Well, the H part is very, very simple. The H stands for hydrogen ions. So, obviously, it's referring to the hydrogen ion concentration, which makes perfect sense. The other part that doesn't make a lot of sense is the P. Now, for years I used to think, well, maybe it's potential hydrogen. Maybe the P stands for potential. It turns out I was wrong. I looked it up. In algebra, we often have unknown variables, all right? And we use a letter to represent those variables. The most common one is x. Solve for x. But a variable, an unknown variable, can be represented by any letter. For example, if you look at, in geometry, when you go and look at the area of a right triangle, you use A plus B plus C. So A, B, and C. In algebra, you can also go and solve for Y and solve for Z. So any unknown variable can use any letter. And in some math, we find that a common ones are P's and Q's. All right? So P just stands for an unknown variable. All right? pH. How many hydrogen ions do we have? Well, that's an unknown variable, and we'll find out. So the P just is a symbolic represented for an unknown variable. So that's what we mean by pH. That's what Sorensen used to come up with his scale. Now, water, which has a pH of 7, is classified as neither an acid or a base. It's classified as a neutral solution. Water is sort of our benchmark in measuring hydrogen ion concentrations. So if the hydrogen ion concentration is greater than water, we say that it's acidic. If it's less than water, then we say that it's basic or alkali. But there's a really interesting form of water that is acidic, and it's rainwater. When rain falls from the sky, and let's say we go out and we collect it in a beaker, and we put our little pH meter in there, or a little litmus paper in there, we go and we find that it has a pH of 5.6. That's acidic. In fact, in that case, we find that that's over 100 times more hydrogen ions than water. That's 100 times more acidic than water. And we go, well, that's weird. Why does that take place? Well, there's a little bit of chemistry that occurs within our atmosphere. And that chemistry is a reaction that happens spontaneously between water and carbon dioxide. Carbon dioxide in the atmosphere. So in the atmosphere, all right, water will mix with carbon dioxide and produce a weak acid. This acid is called carbonic acid. Carbonic acid. All right. The formula is going to be H2CO3, all right, carbonic acid. Now, we come in contact with carbonic acid all the time. Turns out that anytime you drink a Coke or a soda, you're drinking carbonic acid. All right? If you want it in its pure form, then you drink just carbonated water, plain carbonated water, which we call seltzer, has carbonic acid. And that's what makes it taste a little weird. If you've ever tasted seltzer water, you might notice that it tastes different from just regular water. It has kind of a faint sour or tangy flavor. All right. Turns out the reason why is, if you remember, acids taste sour. So seltzer water tastes a little sour. And the reason for that is because it has a weak acid in it, carbonic acid. Now, you might be thinking, well, I've heard of acid rain. Is this acid rain? No. This is from unpolluted rainwater. In fact, we find out that acid rain is not carbonic acid, it's sulfuric acid, or it's nitric acid. All right. So carbonic acid comes from unpolluted air. Turns out that this is how carbon dioxide goes and cycles in the environment. We know, for example, that if we look at our atmosphere, we have several important gases. Most of the gas in our atmosphere is nitrogen. That's about 78%. Right? The second one, as you know, is going to be oxygen. Oxygen, about 21, 22%. The third gas is an inert gas. It's argon. Right? And that's what makes up 99% of our atmosphere. We have trace amounts. Anytime you hear the word trace amount, that usually means less than 1%. So trace amounts of a whole bunch of other gases. We have some water vapor, we have some hydrogen sulfide, we have some methane. But one important trace gas is carbon dioxide. Right? And carbon dioxide, as you know, and you've probably heard it and learned it in science classes, is a greenhouse gas. That means that carbon dioxide, when it receives heat energy, or will take that infrared light energy and re-emit it. Now, thank goodness that we have CO2 in the atmosphere, because it keeps our Earth a lot warmer than it would be. All right? If we didn't have an atmosphere, all right, the temperature of our world would be way below zero. All right, the average temperature would be way below zero. It'd be pretty much tough to be an inhabit. That atmosphere helps us keep us nice and toasty. The other thing it does, it actually goes and protects us from all kinds of cosmic rays coming in and dangerous radiation coming in from the sun. All right, so the world would be a completely different place. So CO2 has helped warmed our atmosphere and kept us nice and comfy. Now, if we look at the cycle of carbon dioxide in the atmosphere, we find that it reacts with rocks and then eventually goes back into the atmosphere. So, where does our CO2 come from? Well, CO2 is part of magma. The molten rock, it's found in rocks. And when a volcano erupts, one of the things that comes out is carbon dioxide. Now, as you know, carbon dioxide in the atmosphere will actually go and produce carbonic acid. And there's our little carbonic acid. Carbonic acid comes down as rain. As a little acid, it'll go and start dissolving substances in the rock. This is, typical chemical weathering that takes place. And eventually that carbonic acid actually goes and makes it into the oceans. Right? Turns out that's a big source of CO2. And in two different ways, sometimes living organisms will do that. They'll take out that carbon and they'll create their shells and make shells. So if you look at mollusks and corals and plankton and crustaceans, they all go and suck this out of the water and turn it into a shell. There's some inorganic processes that will do this too. They'll actually go and take it out of the water, precipitate, and help form rock. Now, the most common rock that is formed with this carbonate is going to be limestone. Right? Limestone is calcium carbonate. It's one of our major sedimentary rocks, and it's made in two different ways. One, when you have a whole bunch of shells that break down and they get sediment piled on top of it and they get heated up and chemically altered, it becomes limestone. So a lot of our limestone comes from old coral reefs and old shells and things like that. It also can be formed through a little chemistry. All right? Calcium carbonate can precipitate out and actually go and form solid rock. So that little carbon dioxide eventually becomes limestone. Now, because we live on a very active Earth with big tectonic plates, that limestone eventually goes and gets subducted, especially if it's in the ocean, will get subducted underneath the continent, and that limestone will go down deeper and deeper and deeper into the earth and melt. And then once it melts, all right, it becomes part of the magma, and then when we have a volcanic eruption, all right, that CO2 is released and goes back into the atmosphere. So this is sort of a long, slow cycle. So this is where the CO2 sort of was born in our atmosphere. It came from rocks. Now, since the Industrial Revolution, since about the 1700s, humans have sort of upset the balance of the amount of carbon dioxide in the atmosphere. Right? We had a balance for millennia, where if you look at this little chart here shows you the amount of carbon that goes up in the atmosphere, the amount of carbon that leaves the atmosphere. If you look, one of the big ways that carbon is removed from the atmosphere is through photosynthesis. As you know, plants take carbon dioxide and use it to make sugar and make their cells and make their bodies, and all life sort of runs on photosynthesis. If you're an animal, you're basically, even if you're the biggest carnivore, all right, if you go down the food chain, you're eventually going to go to a photosynthesizer. So as you can see, it says photosynthesis 110. Now what 110 represents is billions of tons of carbon. So every year, all right, we have 110 billion tons of carbon removed from the atmosphere to make plants. You can see that that is balanced by 110 billion tons of carbon being put out into the atmosphere through aerobic cellular respiration. When you go and feed on a salad or eat a plant or eat an animal that eats a plant, all right, and you metabolize that food, one of the waste products is CO2. You breathe it out. So when bacteria are breaking down a critter or breaking down a plant, they're releasing that same gas. So as you can see, there's a nice little balance there, a carbon balance. Now, volcanoes also go and produce CO2. And as you can see over here, we have about 0.7. So that's about 7 700 million tons of carbon released to that. So we have a nice little balance. Now, something that's happened since the beginning of the Industrial Revolution is the burning of fossil fuels. Our whole entire civilization is built on a huge amount of energies that we can get from burning oil, burning coal, burning natural gas. All right, those big three sources of energy. All right. Basically, that's just ancient photosynthesizers. Oil, gas, and coal all come from not dinosaurs. They come from usually photosynthesizers, algae and plants, all right? And some photosynthesizing bacteria. All right? Basically, a lot of it comes from plankton. All right? So in this case, we are actually taking that and we are releasing all that carbon in the atmosphere. And as you can see, we are releasing 10 billion tons into the atmosphere every year. Right? Now that upsets the balance. That really upsets the balance. And what we've seen over time is that CO2 balance has really increased. So let's take a look at it. This is the famous Keeling curve. In the 1950s, an atmospheric scientist named Dr. Keeling decided he wanted to measure the amount of carbon dioxide in the Earth's atmosphere. He chose a really cool place to do it, a fairly remote place on the planet. If you've ever flown to Hawaii from Los Angeles, it's a 5-hour flight over water. Hawaii is a pretty remote place. And so he thought, well, that's a good place to start. So he set up a measuring device on the Big Island of Hawaii that actually went and measured the amount of CO2 that's in the atmosphere. All right? And he started, as you can see, in 1957. And so over time, and of course, this isn't just from Mauna Loa, which is on the Big Island of Hawaii. We've also put them around the globe. All right? But this is the most famous one. And as you can see, over time, every year, the amount of CO2 has increased. Now, the scale, remember, carbon dioxide in our atmosphere only measures, it's a trace molecule, it's a trace gas, 0.03%. Now, 0.03% doesn't sound like a lot, and it's not. But it turns out carbon dioxide is a big player. It is a very big player because it is a greenhouse gas. Right? It's almost like thinking, let's imagine you go to a University of Alabama football game. Right? That stadium holds about 100,000 people. So you have 100,000 people in there. Right? If you think about who the most important people are in that stadium, it's usually not the fans. It's that 100 or so people, the players, who are down there playing. Right? They represent just a tiny fraction of all those people, but their role in the outcome is huge. Same way with carbon dioxide. It may not be big in numbers, but its role in the warming of the planet is huge because it's a powerful greenhouse gas. So what's happened over time is that we measure it in parts per million. So if we go back to the 1950s, we'll find that it was below 320. In fact, we think that around the start of Industrial Revolution, the parts per million was 270. All right, so when we started burning a lot of coal, and then later oil, and then later natural gas, all right, we've increased the carbon dioxide concentration quite a bit, starting at about 270. And as you can see, this goes and stops at about 210. Right now, in 2017, we were up to 400 parts per million. So we have actually increased in 80 parts per million just within the last 60 years. Right? That's amazing. We've never seen a rise this quick, ever. Right? Now, you'll notice that there are little fluctuations. If you look at the red line, you might be wondering, why does it go up and down? That's seasons. Right? As you know, in the summer, as plants grow, right, they go and suck in carbon dioxide. So the little drop that you see every year is the spring and summer. The rise in CO2 is in the fall and winter when photosynthesis declines. So you're seeing the rise and fall of photosynthesis every season. Now, this chart is pretty amazing. You think, well, okay. But let me show you another chart. This is the very famous, what we call hockey stick chart. All right. This is the one that really made people nervous. Now, you might be thinking, how do we measure carbon dioxide concentrations in the atmosphere, let's say 1,000 years ago, or 10,000 years ago, or 100,000 years ago? Well, there's a way to do it. A couple ways. One really easy way is to look at ice cores. Right? If we go to places with a lot of glaciers or ice caps, places like Iceland, Greenland, northern Canada, Antarctica, all right? If we go to the tops of mountains, for example, along the equator, all right? The Andes, the mountains in Africa, the Himalayas, and we burrow down every time it snows, all right, little pockets of air get trapped in the ice, and they remain there for centuries. So when we get an ice core that's really deep, all right, and some of these are huge. For example, if you go to Antarctica, they're like 14 miles deep. Well, not 14 miles deep, 14,000 feet deep. All right? And so you have thousands and thousands of years of a record, a CO2 record. And so this is how we came up with this particular graph. You can measure the CO2 levels at different places along the planet. And you'll notice here, this goes back about 600,000 years. And if you look at it, there are some natural fluctuations. But you'll notice in the past 600,000 years, it's peaked out around less than 300, around 275. And as I mentioned, at the start of the Industrial Revolution in the 1700s, it was about 275 or 270. But as you can see, the reason we call that the hockey stick is look at the end of it, there in yellow. You'll notice that within just a couple of hundred years, the CO2 levels have skyrocketed. That's pretty amazing. Look at that skyrocketing there. What's going on is that we are now experiencing a rise in CO2 that has never been seen in 600,000 years. No one alive has ever experienced this. We're living in a time where we haven't seen these levels of CO2 in probably 20 million years. All right? So these are just brand new levels that haven't been around for a long, long time. Now, you might be looking at some of these other ones and go, well, I see a pretty quick rise on some of those. The scale is so big that those rises that you're seeing, if you look at the last big rise that starts at about 200 and then goes to 275, that took 10,000 years to do. That's a scale of about 10,000 years. And what we're seeing now is a scale of just hundreds of years. So we've never seen it fluctuate this fast. Now, we all know about global warming. We've heard about it. We have big political fights about it. All right. And we hear about the temperatures rising, the average temperature rising, and the ice sheets melting and glaciers melting and all that stuff. But there's an aspect of climate change or global warming that most people haven't heard of. Now, remember, anytime that you go and add carbon dioxide to water, what gets formed? Carbonic acid. So, as we put more CO2 into the atmosphere, the oceans are making more carbonic acid. As the oceans are absorbing that CO2, they're making more carbonic acid. And what's happening is the pH of the oceans is dropping. The oceans are becoming more and more acidic. More and more acidic. We call this ocean acidification. All right. Now, as the pH of the ocean water decreases, it can still problems for animals and organisms that have shells made of limestone. Right? As I mentioned before, when you look at a clam or a mussel or an oyster, all those mussels, snails, they all have clams and shells that are made of calcium carbonate, same stuff as limestone. If you look at a coral reef, all right, that's all limestone, that's calcium carbonate. And we know how important coral reefs are. They're often the hub and the source for huge biodiversity of fish and other animals and other invertebrates. But one of the most important organisms that actually goes and has a limestone shell are plankton. All right. In fact, we often describe them as calcareous planktons. These little pictures here that you see are all types of photosynthetic single-celled organisms. All right. These actually form the food base for marine systems. So these are fed on by invertebrates and tiny fish. Those tiny fish and invertebrates are eaten by bigger fish. Those bigger fish are eaten by still larger fish. And oftentimes those fish are eaten by us. Right? So it forms the base of the food chain for a lot of organisms. As the pH of the oceans decrease, just like we see on land, carbonic acid dissolves rock. And it will go and dissolve calcium carbonate shells. So, this increase in CO2 in the atmosphere lowers the pH of the oceans. This is what we call ocean acidification. And it does a number on coral reefs. It does a number on anything that has calcium carbonate as a shell. So this includes plankton, this includes corals, this includes clams and oysters. Now what you're seeing here are a nifty type of snail. These are called pteropods. And you're not seeing an adult snail. Usually when you think about a snail, it's crawling along the substrate. Now baby snails, which we call veligers, are planktonic. In marine snails, the baby form, the larvae, are up in the water column swimming around. Right? They're feeding on plankton and things. Right? And some of them have a really interesting foot that has cilia on it that allows them to swim around. And some of them actually go and flap that foot. And they kind of look like little butterflies or angels. These are called pteropods. Ptera just means winged. Of course, pod means foot. And it turns out that these are a major source of food for a lot of our commercial fish. Salmon, haddock, cod, all right, herring. A lot of the commercial fish that we like to eat or use like to feed on pteropods. And it turns out that acidified oceans dissolve the shells of these guys. And so they're at risk with ocean acidification. And of course, crustaceans. If you go and you ever wonder why you have to use a mallet to open up a crab? Right? That crab shell is really hard. Not only is it a carbohydrate, which we call chitin, but it also has embedded limestone in it. It has calcium carbonate in it. And of course, if you're a crustacean and your ocean is becoming more acidic, it's going to eat away at that. So, in addition to problems with global warming, we also run into this problem of ocean acidification. Okay, let's talk a little bit about stomach acid. Most people are under the impression that the reason that we have stomach acid is to digest food. Turns out that it's not true. Stomach acid, particular hydrochloric acid, has one very important role. And that role is to kill bacteria. One of the major entry points inside your body for microbes is the digestive tract. All right? And a lot of microbes can hurt you and damage you. Think about all the people who died over the centuries from infectious disease. And a lot of them are foodborne diseases. So it's really, really important that you kill bacteria before it gets inside your body too deeply. So basically what the stomach is an acid bath. We have hydrochloric acid in there. Those free ions play a havoc with bacteria and kill bacteria. So it's a disinfectant. The main function of hydrochloric acid is to kill bacteria. All right? Now, one of our enzymes actually uses that hydrochloric acid to activate. Inside of our stomach, we have an enzyme that's called pepsin. In fact, pepsin means stomach protein. If you've ever wondered why things called Pepsi, all right, remember, a lot of our soft drinks were created as a health tonic by pharmacists. They were supposed to help your digestion. So pepsin, all right, it refers to the stomach. And it actually goes and breaks down some proteins. Here's a nice little picture of a piece of protein. And as you can see, when you combine hydrochloric acid and pepsin, it works great. All right? Pepsin is activated by the presence of hydrochloric acid. But the big thing about the stomach, about stomach acid, is that it works by killing bacteria. All right. Now, I suffer from heartburn. Probably a couple times a day, I get stomach acid that ends up in my esophagus, and it hurts. Now, oftentimes what I'll do is I'll take Tums, an antacid. Now, antacids turn out to be acid neutralizers. All right? For example, if you remember, an acid has free hydrogen ions, an excess amount of hydrogen ions. If we want to change the pH, if we want to get it back to neutral, then what we have to do is we actually have to go and take up those hydrogen ions. So we add a base. If you want to neutralize an acid, you add a base. Right? If you want to neutralize a base, you add an acid. Right? Back in the 90s was a movie called Fight Club. And there's a scene in it, all right, where Brad Pitt's character actually goes and puts some sodium hydroxide, some lye, on Edward Norton's hand. And it's making his skin burn. It's a chemical burn. And eventually what happens is that Brad Pitt neutralizes that base, that strong base, with vinegar. Vinegar is an acid. So he neutralized, he brought the pH back to normal, back to 7, by adding a base to it. Right? So if you want to neutralize an acid, add a base. If you want to neutralize a base, add an acid. Now, our antacids all pick up excess hydrogen ions. They're all going to be bases. For example, and when I was a kid and my mom would give me a spoonful of milk and magnesia, the principal component is magnesium hydroxide. And as you can see, hydroxide, that's the thing, hydroxide likes to pick up hydrogen ions. And you can see how it gets neutralized, and we end up with magnesium and some water. Now, my favorite is Tums, and Tums is just basically calcium carbonate. And as you can see, what goes and bonds to it is the carbonate ion. The carbonate ion goes and bonds with the hydrogen and produces water and CO2. Alka-Seltzer, which is another antacid, is sodium bicarbonate. All right? And as you can see, the carbonate, which acts as a great little base, goes and picks up the hydrogen ions and neutralizes them. Digel is a lot like milk and magnesia in that instead of magnesium, it has aluminum. So aluminum hydroxide, and of course the hydroxide picks up the hydrogens and makes it into water. Now, the most complicated one is Rolaids, and Rolaids, it's pretty amazing. If you want to neutralize your acids in 2 ways, with 2 separate bases, that's the way to do it. You'll notice that it has hydroxide and it has carbonate. So the hydrogen ions are picked up by both those bases, hydroxide and carbonate. So Rolaids, if you want to get rid of the hydrogen ions in 2 ways, give it both barrels, that's the way to do it. Now, in our blood, we have a very, very narrow pH range, 7.35 to 7.45. All right? And we have to keep our blood within that pH range. Outside those ranges can be very, very dangerous. In fact, if the blood becomes too acidic or too basic, it can kill us. It can be lethal. Now, we are always being introduced, and certain types of chemical reactions are occurring in our bodies all the time that fluctuate on pH. Now, in order to prevent big fluctuations in pH, we have within our bodies what are called buffers. Buffers are substances that help prevent big pH fluctuations. How a buffer works is that when, for example, it's exposed to an acid, usually a buffer is a combination of 2 things. It has a weak acid and a weak base. In fact, oftentimes it'll be an acid and then what we call a conjugate base. Basically the same thing, but with less hydrogen ions. So it has these 2 molecules, a base and an acid. And so when a body fluid gets too acidic, the basic part will go and start absorbing those hydrogen ions. and raise the pH. If a body fluid goes the other way, if it becomes too basic, then the acid part will start releasing hydrogen ions to bring the pH back to neutral, or back to its normal range. All right. So that's what buffers do. In fact, our most common buffer system that we have in our blood is one that we call the carbonic acid carbonate system. All right. It has carbonic acid, which is an acid, and it also has bicarbonate, which is a base. So when our blood gets too acidic, the bicarbonate absorbs that excess hydrogen ions. When our blood becomes too basic or too alkaline, then the opposite happens. The hydrogen are released by the carbonic acid. All right? And it helps keep systems within a very, very narrow range of pH. Now, the reason why that's important, when we get to enzymes, when we talk about how enzymes run the body, they're the resident chemists of the body, they are incredibly finicky. And enzymes will only work at their optimal conditions within a very, very narrow range of pH. This is why blood has to stay within 7.35 to 7.45. All right? So buffers are important systems. And when you take anatomy and physiology, you'll learn about these buffer systems that we have in the blood. All right? So this is just one. We have a couple other ones, but very useful in keeping the pH at a narrow range. Okay. We'll go ahead and stop here, and we'll be done with acids and bases and pH.